All right, you guys, let's start talking about introduction to normal distributions. So what we're going to do in this first video is just learn a little bit about the normal probability distributions, especially talking about what's called the standard normal curve. And we're going to start finding areas under this so-called standard normal curve. All right, so what are the properties of a normal distribution? Well, first of all, we're going to be looking at a continuous random variable. All right, so what do we mean by continuous random variable? Hopefully this rings a bell from last week. All right, a continuous random variable has an infinite number of possible values that can be represented by an interval on the number line. In other words, it's not discrete, which means it's not countable. All right, so here we have hours spent studying in a day. You would say, oh, but Angie, that's countable. I can count the hours. But there's infinite minutes and seconds in between hours, correct? Absolutely. All right, so that would be a continuous random variable. All right, a continuous probability distribution is just going to be a probability distribution of a continuous random variable. All right, so what about a normal distribution? Well, this is going to be a continuous probability distribution for some random variable x. All right, is that it? No, it's got to have some more features. All right, the normal distribution, first of all, is the most important continuous probability distribution in statistics. We use the normal distribution when pricing stock prices, when pricing stock derivatives, so things like options. The normal distribution is used all over the place, especially in economics and finance. All right, the graph of a normal distribution is called the normal curve. And this should look familiar. This should remind you of when we were talking about the empirical rule. All right, so again, we're going to call this the normal curve or normal distribution. All right, what do we know since it looks symmetric? Well, we know the mean, median, and mode are equal. All right, the mean is right there in the middle with the median and mode. The normal curve is indeed bell-shaped and is symmetric about the mean. What does it mean to be symmetric about the mean? It means if I were to fold on that dotted line in the middle, that each half ends up on top of the other. The total area under the normal curve is equal to 1. All right, this is not something you need to try to memorize. It's just something that's common sense. Remember, we're dealing with probabilities. What do probabilities for a distribution have to add up to every single time? You got it, 1. All right, meaning under this curve is 100%. All right, and the normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. All right, let's think about this in terms of our NBA salary data from Excel 3. All right, hopefully we can recall that the mean was somewhere around $5 million. All right, but we know that there's LeBron and Kobe. We remember Kobe was up there around $23.5 million. All right, if this data were normally distributed, then we're always having room for somebody making 60 million, 100 million, all right, meaning we can always have outliers further and further away. All right, this is an interesting characteristic of the normal distribution we want to think about a little bit. All right, so bear with me as I try to explain it, and I think I'm going to go ahead and grab my pen because as a teacher I have to have a pen in my hand to talk. All right, between mu minus sigma, all right, so this means between the mean minus 1 standard deviation and the mean plus 1 standard deviation, the graph curves downward. Okay, the graph curves upward to the left of the mean minus a standard deviation and to the right of the mean plus a standard deviation. The points at which the curve changes from curving upward to curving downward are called inflection points. All right, so what are we talking about here? Okay, so let's consider 1 standard deviation away. Between them, we're curving down. On the outside, so to the left of the mean minus the standard deviation, we curve up. And to the right of the mean plus the standard deviation, we curve up. So these points at which we're changing how it curves, whether it curves up or curves down, are called inflection points. And at these changes in concavity are where we are one standard deviation away from the mean. All right, so again, what am I saying? If we go one standard deviation away from the mean, we will find that the curve is changing. It changes from curving down to curving up. All right, a normal distribution can have any mean and any positive standard deviation. We've seen this especially with IQ scores. The mean is 100 and the standard deviation is often reported to be 15. The mean gives the location of the line of symmetry. Line of symmetry is just that dotted line I was referring to in the middle where we can fold and get the two halves on top of each other. The standard deviation describes the spread of the data. All right, so how is our distribution spread out? Is it really wide or is it really narrow? All right, so let's look at these three distributions. All right, here we have something close to what would be somewhat of a normal distribution. All right, so we have our line of symmetry right here at 3.5, and we notice that we change from curving down to curving up around 5 and 2. So here we can see our mean is about 3.5 and our standard deviation is about 1.5. How am I getting that? Well, I'm moving about 1.5 on my number line to get to this inflection point. Okay, so I'm going to say sigma equals 1.5. And our mean was 3.5. 3.5. Okay, what about graph B here? All right, well again, we can see our mean is right here at 3.5. Okay, 3.5. All right, and what about our inflection points? Well, our inflection points now are occurring at 2.5 and 4.5. All right, so if our mean is 3.5, to go to that first inflection point, I'm only moving one spot. So my sigma here is going to be a 1. In other words, graph B has less standard deviation than graph A. That makes sense, doesn't it? Isn't graph B kind of tall and narrow, whereas graph A is kind of flatter and wider? All right, let's look at graph C. Graph C, all right, where is our line of symmetry? It's right here at 1.5. So for graph C, mu is going to be 1.5. All right, what about sigma now? Well, my points of inflection are occurring again about one place away. All right, so here sigma is equal to 1. So basically, all I did to get graph C is I took my distribution B and I moved it down to where the mean is 1.5 instead of having a mean of 3.5. All right, I'm just beginning to show you guys a little bit of how we can have different means, different standard deviations, and certainly how the standard deviation changes the shape of the distribution. Okay. All right. Which normal curve has the greater mean? All right, so below we see two symmetric distributions. All right, which one has the greater mean? What are we looking for? All right, what we're looking for is the line of symmetry. Note on B, the line of symmetry is around 12, whereas on distribution A, the line of symmetry is around 15. So curve A has the greater mean. Which curve has the greater standard deviation? All right, well, notice here's an inflection point for B, here's an inflection point for B. Given the mean, we can see that the standard deviation is roughly 3. Okay, let's change our color for curve A here. So curve A has a mean of 15, all right, with, all right, an inflection point roughly about here, all right, and that looks like it's probably going to be maybe 1.5, all right, so a standard deviation of 1.5. Right? And I'm just guesstimating here, guys. It's not an exact science because right now all we're trying to do is figure out which curve has the greater standard deviation. And clearly, by looking at the numbers, at the line of symmetries with the inflection points, we see that B has a greater standard deviation. Is there a more obvious way to see that? Sure there is, because there's a big discrepancy in how A and B look. B is really flat and spread out wide, whereas A is a tall, narrow curve. All right, and so that's just another way of telling us that curve B has a greater standard deviation. All right, let's talk about interpreting the graphs a little bit. The scaled test scores for the New York State Grade 8 mathematics test are normally distributed. The normal curve shown below represents this distribution. What is the mean test score? And estimate the standard deviation. All right, well, for the mean test score, what are we doing? We're looking for the line of symmetry, right? All right, sure we are. And we can see that the line of symmetry here in the middle, all right, is roughly around 675. All right, so we're able to estimate based on where the line of symmetry would be in the middle of the hump that mu is about 675. What about the standard deviation? How are we going to estimate that? Well, you guys, we're looking for the inflection points. All right, and we can see where we're changing from curving down to curving up. All right, where we are 1 standard deviation from the mean. All right, and we can see here that the standard deviation is approximately 35. How do we get that? Well, I'm going to subtract 675 from roughly about maybe 710 or so, and I'm going to get a standard deviation of about 35. All right, let's talk about the standard normal distribution. All right, a standard normal distribution is simply a normal distribution with a mean of 0 and a standard deviation of 1. All right, instead of having an x-axis of, like, say, IQ scores or something, or hours spent studying, something like that, now we have a z-axis of z-scores. All right, so again, 0 is the mean. All right, and we're looking at 1 z-score above the mean, 2 standard deviations above the mean, 3 standard deviations, and so forth. Any x value can be transformed into a z-score by using the formula that you guys already know. All right, we did this with Kobe Bryant's salary. All right, z is equal to the x value minus the mean, all divided by the standard deviation. All right, if each data value of a normally distributed random variable x is transformed into a z-score, the result will be the standard normal distribution. In other words, we can standardize any normal distribution. All right, so here, notice I have, say, maybe IQ scores or some other x continuous random variable. I can use my z-score formula to transform all of these x values, and I'll have my standard normal distribution where now my mean, say, instead of being 100 like with IQ scores, would be 0. Instead of having my IQ standard deviation of 15, I would now have a standard deviation of 1. All right, the reason you'll hear about the standard normal distribution is once upon a time we had textbooks. And with especially with statistic books, in the back there was something called a standard normal table. All right, and we used to have to go through this long process of looking up z-scores, finding probabilities under the curve, all right? But now we use something beautiful called Excel, and I'm going to show you guys in just a minute how we're going to go about using Excel. All right, so what are the properties of the standard normal distribution? Let's just talk about some of the basic properties here. The cumulative area is close to 0 for z-scores close to negative 3.49. All right, what's the English of this? The English is saying that once we get to negative 3.49 standard deviations below the mean, so we're at negative 3.49, our probability is darn near close to 0, okay? The cumulative area increases as the z-scores increase. Remember, this whole light blue shaded area has to equal 1. So as we move up in z-scores, we're moving up in area or probability. All right? The cumulative area for z equals 0 is 0.50. All right, meaning if we're at the mean, all right, 50% of the data lies below it. Well, duh, we're at the mean, we're in the middle. All right, that's all that's saying. All right, that when we are at 0, in the middle, at the mean, the light blue area is 0.50. All right, the cumulative area is close to 1 for z-scores close to z equals 3.49. So now when we go all the way to the right, all right, once we get to 3.49 standard deviations above the mean, our area or probability, we can say, is pretty much 100%. All right, it's 1. In other words, I could say, what's the probability an NBA player makes less than Kobe Bryant? Well, recall his z-score was 3.82, so it would have been 1 had we been dealing with a normal distribution. All right, you see how hideous this looks, guys? This is what I was talking about with those standard normal tables. You used to have to flip to the back of a book, figure out how to read this. Students had a harder time learning how to read these charts than actually understanding what the heck they're doing. So I say we're going to throw it out and we're going to use Excel instead. Okay, so I'm going to come out of here, and what we want is the z-score of 1.15. Okay, so I'm going to open up Excel, and I claim Excel has a way we can do this. I'm going to say area to the left of 1.15, and I better say z equals, just so those of you who go back to this remember what I did. All right, so we want the area to the left of z equals 1.15. Okay, we have a function in Excel, and you see it just popped up here, norm.s.dist. All right, so that's telling me to get the area under the standard normal distribution, so norm.s.dist, all right? And we have to input a z-score, and we're going to say comma true, meaning we want it to be cumulative. So I say 1.15, comma true. And you can see I got the probability of 0.8749, which is exactly what this hideous table gives over here in the old-timey way. Okay, now how do I know it's the area to the left and not to the right? All right, anytime you use this function, you're always going to get the area to the left. Okay, so just like our picture here shows, all right, this light blue area, all right, is all the area to the left of 1.15 is what we get from using this function. Okay, all right, let's try another one. Let's consider negative 0.024. All right, so now we want negative 0.2 0.24. All right, so I come in here and I say equals norm. There we go. There's our, oh, Angie. All right, norm.s.dist. We want negative 0.24. I always have to say true. All right, and you can see, just as I'm showing you down here with the old-timey table and the graph, all right, we get our area or our probability as 0.40. I'm using area and probability interchangeably. That's what that shaded blue space is. Okay, so let's talk about interpreting this a little bit. All right, so to the left, okay, so the area to the left of negative 2.4 standard deviations is 40%. All right, so let's try another one. All right, finding the area. All right, let's find the area, all right, to the left of some z. Let's use, all right, now we're looking at z of 1.23. All right, why am I doing it in Excel, guys? Because it is so much quicker and easier, and you really should have an Excel spreadsheet up when you go through your homework. All right, so let's do equals norm. All right, there's my standard normal. I'm looking for 1.23. Always type true, and the area to the left is 0.890. We'll round up 0.8907, as we can see from this chart. So again, if I want the area to the left, all I have to do is type in my function norm.s.dist, put in my z-score, and type the word true. Okay, now let's start making it a little bit more difficult. Now I want the area to the right of 1.23. So now I want the area to the right of 1.23, and this is where you have to use what you know about the standard normal curve. The total area is 1, and so we need to do 1 minus the probability to the left. All right, so if I want the probability to the right, I'm going to do 1 minus norm.s.dist and 1.23 comma true. All right, so here when I do 1 minus, again, it's because I want the area to the right. If I just did norm.s.dist, we know from above I'm going to get 0.89. All right, that's the area to the left. I want the area to the right. So again, I type equals 1 minus norm.s.dist, and you can see that I'm getting 0.10934, all right, which is going to be the area to the right. Notice if I highlight both of these, you can see from down here that I'm summing to 1. That's the total area. If I add the area to the left of 1.23 to the area to the right of 1.23, then of course I'm going to get 1 because I know the area under the normal curve is 1. Okay? All right, so again, just so you remember, this is going to be 1 minus norm.s.dist. Okay? All right. What about if I want the area between two z-scores? So I want the area between z equals negative 0.75 and z equals 1.23. All right, so how am I going to do this? Well, if I were to just get the area to the left of 1.23, I'm going to get everything to the left. I don't want anything to the left of negative 0.75. All right, so how are we going to do this? We're going to do equals norm.s.dist. All right, and I start with the one furthest to the right, 1.23. All right, so if I were to do enter right now, then clearly I get the entire area to the left of 1.23. I want to stop at negative 0.75. So what am I going to do? I need to subtract norm.s.dist at negative 0.75, comma true. All right, and you can see I'm now getting the area between negative 0.75 and 1.23, because when I subtracted the area to the left of negative 0.75, I subtracted away this pale yellow area, leaving me just with the blue shaded area. Okay? It's going to take some getting used to. That's why I'm offering 3 study sessions this week for you guys. All right, let's find the area under the standard normal curve to the left of z equals negative 0.99. All right, so we want area to the left of z equals negative 0.99. That's an easy one. That's a straight up to the left. So norm.s.dist, negative 0.99, always true, not pure. All right, and I get 0.1611, all right, as my area to the left. All right, what if I want the area to the right of z equals 1.06? All right, now I want the area to the right. So now I have to do 1 minus norm.s.dist of 1.06, always true. And you can see that I'm getting the area now to the right, which is 0.1446, roughly rounded. Okay. And lastly here, let's do one again between. So I want the area between z equals negative 1.5 and z equals 1.25. So this is where I do equals norm.s.dist. All right, I start with the one furthest to the right, 1.25, and I have to subtract the area from the lower bound of negative 1.5. And Angie clearly made a mistake. I did not do negative there. Okay, okay, this is a great teaching point. Let's go back in here. How do I know I made a mistake? All right, if this were to happen to you in Excel, well, that says the area is negative, or the probability is negative. How many negative probabilities have you ever seen? All right, well, it's impossible. All right, it's impossible to have a negative area. So I know I made a mistake, and I see, well, I didn't type my negative 1.5, and now I'm able to get my area between my two z-scores of 0.826.